All right. So this is a very interesting topic. So we talked about this tracker, right? The single one infrastructure node, which tracks, which basically tracks the information about all the files, and for each file it tracks the number of the list of peers that hold this file, right? This is that huge infrastructure node that everybody has to contact. And imagine that you're running the system across a vast number of files and users. Uh, this node has to be a super node, right? It will potentially not scale because everybody will keep going to this node. So ideally, you want a distributed design for this tracker. Like you don't want to create one super node where everybody goes to. So the idea is that this table, you can think of this tracker as holding this table with on the key. The key is the file name, and the value is basically the list of IP addresses of peers who have this file, who's involved in the exchange of this file. So this table, you want to be able to distribute this table among a set of people so that there's no one central bottleneck. That's the goal, right? Now, with that in mind, let's discuss distributed hash tables, which really came as a solution to this problem. So basically, you can think of this tracker as one hash table, which tells you which has rows of this form: file name and list of IP addresses. And the idea is that what if we can distribute the hash table among the peers themselves? Then it's easy, right? So then you don't need one node. Uh, still everybody can sort of ask everybody else to get this hash table. So such a distributed design of this hash table will be a distributed hash table. Okay. So is that all? Does it mean that there is no bootstrapping required here? So is there any info? So let's say a new machine joins a P2P system. What information does it need, even if the table is distributed?
It still needs to know where to start because
At a bare minimum, it has to know one other peer, right? So let's, for the time being, assume that there is some way where somebody will just provide this one information that, hey, this is this one guy whom you will talk to, but that's it. You will after that, for example, when you enter or leave, or as you get more chunks, remember you should also inform the tracker of what chunks you have, right? So that information, you don't have to go to the central guy. All right. So you want to, the goal is to distribute this key value pairs among the peers themselves. That's the goal, right? So the key in this case, the key is actually the file name, and the value is the BitTorrent peers, right? BitTorrent tracker peers, and each peer holds a subset of keys, right? Because uh, this is basically a list, right? And it's also possible that the entire list uh, is not in one peer. So in which case you'll have to sort of go through multiple, right? So the distributed hash table will have the standard semantics as any other hash table, right? Any hash table you sort of basically have two APIs, right? It'll provide you a get and a put, right? You should be able to get any item and you should be able to sort of update any item, okay? So the same thing holds here. So in this DHT, you can query for a particular key, right? Key in this case would be a file name, right? Or you can also update the key, meaning you can update, in this case, let's say a new peer has now holds the file. It can update saying that, hey, I am one of the peers who has this particular file. All right. So this in general, if you have done any hash table implementation, you will also know that typically the key is some sort of a number. It's a numerical value. You will not deal with, even if the key is an actual key is a alphanumeric key like file name. You want to sort of convert that to a number because ultimately this is the storage table, right? And you want to index this table. So that is a number. The index is a number. So you would want the mechanism to be able to convert any non-numeric keys to an index, right? So for that, you will typically use well-known hash functions, right? Or you can write your own. There are some properties that you might have to sort of be aware when you're designing the hash functions. That is outside the scope of this class. But one general property is that it should it should disperse the file names to as many entries as possible. It should not put everything into the same map everything to the same number, right? So here's an example of how, for example, you might have a hash table of names and phone numbers, right? No, they're not phone numbers; they're social security numbers. And you might, if you're designing a hash table, you might want to go through this intermediate step where you're actually converting the original key into an alphanumeric key. Okay, an example, and we'll do this. The DHTs that we are talking about, they'll also do the same thing. The file name has to be converted to a number before you can sort of store into a table. So the key challenges in the distribution of in designing the distributed version of the hash table is how would you distribute the keys, right, among the nodes? Because that's the goal. Remember, the goal is you have some nodes, some number of nodes, and you want to distribute the key. In this case, the file name, among the nodes, right? So basically, what I mean by that is that it's not that it's not that a particular node stores that file. It stores information about that file. So let's say if it's a movie that you're interested in downloading and you join the P2P system, you should know whom to ask so that you can get information about the list of people who has the copy of this movie, right? And the first question, to whom to ask, that will be determined by the hash table, because you will do a search, right, or the query based on the file name, and it will return you a number. Of that number potentially will identify the peer, and you can go and ask it. That's the idea. Okay. So the one naive option is, why do we try to do this in a systematic way? Why can't we sort of randomly assign? What if you randomly scatter keys, among the peers? Yeah.
You may have a large amount of keys and an unreliable pair.
No, random is always great, right? Uh, if the random number generator has good entropy, you will get uniform distribution. That's not the problem. See, the problem is, think what you will have to do. If you randomly do, let's say you randomly assign the key value pairs. Again, I'm emphasizing, what is the key value pair here? Here the key value pair is, key is the file name. The values are the list of IP addresses, which the list of peers which have this particular file, right? If you randomly assign this particular row of the table to a random peer, how do you know whom to ask? So you'll have to do a broadcast. You'll have to ask everyone to tell me, hey, do you have this info? And then they'll have to respond, and then you can proceed further. So it could work, but it's like, it sort of defeats the purpose. It's not scalable because broadcast is not scalable. Okay? So that's a bad idea. So you want to be able to map the keys in some deterministic fashion. Okay? So here, what are the pros and cons? One simple way of doing the deterministic fashion is that you can take the hash function of the key. This is a different hash function than the function that you use to convert the file name to a number. Think of this as a different hash function. So imagine that you have some function, you are applying the function on the key, in this case, and then it gives you some ID, right? And then you can ask that guy, and you can say, okay, whoever is the node corresponding to this ID, he is responsible for storing this particular row of the table. So you can always deterministically ask that person. But will this work? Why not?
This node ID, I'm guessing, will be a single single
think of node ID in this case is actually an IP address. Think of that.
right. If it's going to
So one thing I have not mentioned, which I should have, I did, but I did not make this explicit. Here, the central assumption is that you have some space of node IDs. Imagine that this node ID space, right, is a number on a range between 0 to n, okay? And in this space, you are mapping all the IP addresses of the peers into this space. But into this space, you're also mapping the files into this space.
what if there are no
So
users
remember,
in
so
that
this is the
space?
mapping function that maps the file names to this number space, IP addresses to this number space. That's how you're able to make this association, okay? With this assumption in mind, why will this not work?
There might not be any users in that IP range, or that IP range might actually get taken down for something.
Exactly, the peers, right? It's quite possible that the IP addresses of the peers that are involved in the exchange of the file are such that there is no IP address that will hash to the same location as the file itself. Is it clear? Right. So obviously this kind of deterministic match will not work, right? So we will do what we always do, which is like a ugly but workable approximation of this. That is, you don't really store the key in the node that is specified by the hash function of the key, but you will store this this information in the node that is closest after taking the hash function. So imagine that you have a file, you apply this hash function, it will give you a number between 0 to n. And for example, let's assume that number is 10, okay? Now, if there are no other peers who map to that 10, you will store this information on the peer who's, the closest number to this 10. And it has to be a little more precise. So it's the closest successor, so the one that is larger. So if there's somebody who's 11 or 12 or 13, whichever is there, you will pick. And then you will put that information into that person, okay? So that's the first point. And then, to rehash this, so the rule is you assign key value pair to the peer that has the closest ID, okay? And in this case, the closest is defined by the immediate successor of the key, the closest successor of the key. Okay, so as an example, let's say that you have an ID space going from 0 to 63, right? And imagine that you have 8 peers whose IP addresses seem, in this case, whose IP addresses happen to map to 1, 12, 13, 25, 32, 40, 48, and 60, okay? Because you only have eight peers. You can't control how many you have. Now, let's say you have some file name that that maps to 51, right? Now, that file name's information will be assigned to the peer 60 in this case, because 51's closest successor is 60, right? And if you have a file whose ID happens to be 60, then you will assign to 60 because it exists. If it's 61, you will assign to 1. It's a circular. You can think of that range as circular. All right.
What happens if 52 happens to, nodes with whatever node ID 52 happen to come up late? When you actually start.
Good question. So the table has to move. So it has to update. So for example, if a new peer joins, some rows of this table have to be reshuffled so that you're maintaining this notion consistent. Any other questions so far? Sorry?
What happens can you repeat the question? What was the question? What was your answer?
Okay, his question was, imagine that another peer joined, okay? Let's call it 61, right? Imagine if 61 joins later. Right now, you have assigned the key 61 to peer 1, right? But if 61 joins, that information has to move to 60. So whenever a peer joins, this hash table has to reorganize itself. But the beautiful thing about distributed hash table is that the amount of keys that you will have to move whenever a new person joins is bounded to a very small number. There's a theoretical bound on it. So actually, this is perhaps the technically the most interesting part of the class that we have discussed so far. So there is the nice paper on this that I have put under as a reference, by the way, in the running schedule. So you guys should all read it. It's fantastic. All right. No, it's load independent. It's totally based on the numerical values. That's again very good question. So that's one of the downfalls, you may say, of DHT, that it doesn't respond well to load. All right. So now, how do peers get their node ID? I have already answered this question. That is, you use the hash function. It may not be the same thing. It can be a different thing. But the function should still map from ID space to key space. Okay. And because we are mapping both the objects, in this case files, and the peers consistently into the same space, the 0 to n space, right? You can actually theoretically calculate the bounds for how much you'll have to move when things change. Okay, so you only have to move a very small subset. I'll comment on it a little later. So so to find a value, you can ask the nearby node, right? And it's a ring, right? So long as you know your successor, you can keep on asking, and finally you will find a match. So that's the idea, okay? So in this circular DHT, each peer is only aware of its immediate successor and predecessor. Okay, so every peer only knows who's the successor, who's the predecessor, and so you can think of these peers itself, they themselves forming an overlay network, right? In this case, it's an overlay network because it's not a real network. The connectivity between them, the actual connectivity between them, may go through sort of multiple routers and multiple network infrastructure, but for logical purpose, you can consider them as forming an overlay network, okay, a ring type network, okay. So just some definitions. So overlay network is a network made up of virtual or logical links, not actually physical links, okay. So one of these virtual links may map to more than one physical links. So in this case, if you go back, the link between 1 and 12 may actually go through multiple physical links, but we don't care about that for the time being, right? So let's see how a query gets resolved. That is, you want to sort of some node wants to find some information about a particular file, a key. Let's figure out how it can find that. Okay, so let's say 12 in this case wants to find out the value associated with key 53, right? So it knows only it's about its successor, so it will ask node 13, right? Node 13 will ask node 25. Everybody knows their successor, so the query goes around the ring all the way to 60, right? And then 60 is the actual one which will hold the key in this case, right? Obviously, because that's the immediate successor. Then the value is returned, right? So I've obviously made this assumption that every peer knows about its successor and predecessor, which is not a lot, okay? Because that you can bootstrap when you start.
And the values returned.
Sorry?
Is the return direct? That's exactly what I was going to ask. Is that returned directly, or does it go back through 48, 40, 32, all the way to 12?
So that depends on the implementation. I think you can go directly.
Okay.
Yeah. So actually, going directly is probably the easiest.
All right.
Otherwise, the message has to carry the path back. Anyway, now if there are n peers involved in the circular ring, right? You need O of n messages, right, to resolve the query in the worst case. So that is not. I mean, it will work. Like this design will satisfies all our assumptions. It's a distributed hash table. Not one node is responsible for storing the entire hash table, but every query still requires you to ask everybody, O of n in this case. So that's not really good. So how can we cut down this search space? Sorry? Correct, exactly. What is the technical, what do you call it?
Binary research.
Yeah. So you will use, so the same tricks, you will apply the binary search trick, and then you can cut down this number of the search complexity to from n to log n. Okay. Awesome. So basically, if you want to do something like that, you need a DHT with shortcuts, right? So each peer not only knows its immediate successor and predecessor, but it should also know somebody more, right? So as an extreme example, you can have you can assume that this is every peer knows multiple shortcuts, right? In this case, every peer has two shortcuts. Okay. So let's say the 12 wants to look up for the key 53. Now it has this shortcut, so it doesn't have to go to 13. It can directly go to 32, right? Go to 48, 60, and then it can get returned. So you can cut down the number of messages from 6 to 3 by having shortcuts. So obviously, if you it's possible to design shortcuts with O of log n neighbors, right? And then you'll get log n complexity. So basically, the idea is that you maintain the neighbor who's one distance away, who's two distance away, four distance away, and so on and so forth, all the way to log n. Yeah.
So you can maintain the neighbors, so you're also dealing with, I guess, dynamic programming, you have, instead of binary search then? Or no? So that's just switch.
Sorry.
Are you using dynamic programming at the point then?
Well, in this case, it's
I mean, it's a step away, isn't it? From
yeah.
binary search, okay.
Yeah.
Need not always be a circle. In this case, you know if it's a circle, the other shortcut.
No. What is there's no circular like this.
Mathematically representing this, the shortcut makes sense here. Like, what if the other?
No. You should not jump. For example, that's a very good question. Let's say you're looking up the key 40, right? What you will do? Let's say the 12 is looking up 40. 12 will take the shortcut, go to 32, but it should after 32 it should not take the shortcut to 48. So you are storing shortcuts which are at a distance of 1, 2, 4, 8, 16 like that, right?
What I was asking is, what if 32 didn't have information about 40?
No, you have information that it's 32, right? The moment you have shortcuts, what do you know? You know that my successive nodes are 13, 32, right?
Yeah.
You know two successive nodes, right? So you know 32. And imagine let's for simplicity assume let's for as an example let's assume that 12 had one more shortcuts to 60, right? In this case, the 12 will have links to 13, which is the immediate successor, 32, and 60. Okay, and let's assume that 12 wants to look up 48. It should not send the query to 60, right? It should only send it to the one that is lesser. Like when it's going through its shortcut list, it should send to the largest shortcut that is less than the key that you're looking for. Yeah.
So, similar question to earlier, but when you add a new peer, is this shortcut list then updated then?
Yes.
And does that take a long time to update?
The more shortcuts you have, the longer it takes to update. So that's a very, very good question. So if you have only successor and predecessor, your search complexity is O of n. But whenever a peer joins or leaves, which is whenever you want to update the links, the complexity is O of n. That's O of 1. Because you only have predecessor and successor, so maximum you'll have to change is 1. O of 1. The update complexity is O of 1. It's constant. The search complexity is O of n. Right? Now, if you have shortcuts, you will cut down the search complexity, but you will increase the update complexity. So there's a trade-off involved. So in the worst case, you can have O of 1 search, right? By remembering everybody. But on update, you will do O of n because you have to update everyone, right? So the binary search is a very interesting point in this space because it gives you O of log n for search. It will also give you O of log n for update because you're only storing log n entries.
Of 1 or of long.
O of log n. So both search and update are log n.
For a new entry, it's log n.
Yeah,
But the circular tree is in ascending order, right? So DHT.
yeah.
So if an entry comes like 47, so it would be arranged.
No, that is for arranging. But you'll have to tell everybody to hold the shortcuts, right? The moment you have shortcuts, and every time you add a node into this tree, everybody's shortcut lists may have to be updated.
So that complexity will increase.
That will increase. So the moment you have shortcuts, you'll have to update more, but you will search less. That's the trade-off. Cool. So, so obviously this log n seems to sort of work really well in practice. That's what I was trying to get. That remembering shortcuts with which are exponential distances apart, which will cut the search to log n with an update also to log n. So that is a good thing. All right. So now, right? This this I already discussed. Going the login, remembering login shortcuts and doing a binary search. So this is what is discussed in the paper that I have put in the schedule. Okay, so you guys should all read it. It's one of perhaps the most influential papers in the last. I would think I don't know maybe in the last 10 or 15 years. But you guys should read it because the paper is called as Code, so it will describe this system, and it had a lot of impact in the P2P space. So you guys should read it. So now let's discuss about peer churn, which is the peers may come and go, right? So you'll have to update. So how it happens, right? So let's take this simple DHT, right? And let's also assume that each peer knows the address of 2 of its successors, okay? Not just 1, but 2, because your successor may leave, right? So then you'll be unconnected. So you need to have 2, right? Now you can obviously ask the question, what 2 of them fail at the same time, right? So you'll have to, how many you'll have to remember, you'll have to figure out based on the failure rate. So when you imagine that each peer remembers 2 of its successors, immediate successors, and it sort of keeps periodically checking them whether they are alive. Okay, and if an immediate predecessor, if the immediate successor leaves, right, it can choose the one after it as its immediate, right. So an example here is that imagine that in this DHT the peer 5 dies, right. So peer 4 prior to that knows about 5 and 8, right. So when 5 dies, 4 asks 8 who is its immediate successor, in this case 10, and it updates 8 as its immediate successor and updates 10 as its the next immediate successor. Okay. So I also mentioned that when I started this discussion, I told that you maintain both the successor and predecessor, right? So just like you're remembering 2 successor, if you want to go the other way around, you have to also remember the 2 predecessor. So the way to think about this is it's a linked list, right? So if you maintain both the successor and predecessor, and everybody maintains that, you can also go around the ring, not in n, but by n over 2, right? Because it's a doubly linked list. But then on update, you'll have to update both the links. It's just something to remember. So now let's see what happens if a new peer joins. In this case, 13 joins, right? So assume that it knows about peer 1, right? So it has to know somebody because then it doesn't know whom to contact. So it has to know somebody. In this case, let's assume that it knows about peer 1. So it sends the message to peer 1, and it wants to know who will be my successor and who will be my predecessor. That's the information it wants to know. So the message that it sent to 1 will traverse the ring. It will come from 1 to 3 to 4 to 8 to 10 to 12, right? And then at that point, the message will carry the number 13, right? The ID of it. So 12 will realize, okay, 13 has to be its immediate successor. So 12 then informs 13 that, okay, I am your predecessor, right? That's how 13 knows that 12 is the predecessor of 13. And 12 also tells who is the successor to 13. So before 13 joined, its successor was 15. So it can tell 13 that my successor is 15. And then, 12 will make 13 its successor. And it will also 13 will send a message to 15. And, 15 will make 13 its predecessor. So the link, the entire, the integrity of this ring is maintained at the end of it.
Basically, 15 and 13 will have as a predecessor 13 at one point, right?
Sorry?
15 and 13
Uh-huh.
at one point will have 12 as a predecessor at the same time.
Correct. So basically, before 13 sends a message to 15,
Then,
15 would have thought that its predecessor was 12.
okay.
So there is a small time during which there is the ring is not consistent.
All right.
So it's a very, again, atomicity questions, right? It's sending a series of messages. At the end of this complete cycle, the ring is correct.
Mm-hmm.
But in between some of these steps, the ring could be wrong. So obviously, if both of them have their predecessor as 12, then the ring is broken, right?
Right.
So here I am assuming that this is one atomic operation. So you see what I'm saying? So when 13 joined, you will have to block everybody from doing anything and then do these changes and then
And then be able to do it. Okay.
yeah. But in practice that you won't be able to do, right? Because you won't be able to block everyone. So during that time, somebody can experience mistakes.
Okay.
But again, probability, right? The probability of that is low, so you're fine. All right. So that brings me to the end of this discussion on DHTs, right? I have sort of glossed over the details of this. This is not in the book, by the way. The whole idea of DHTs and this querying and over to and all that. But I wanted to include it because it's a strong technical material. So I expect you guys to read that paper, okay? And perhaps on Friday, right? I will try to go over some of the more nuanced details from that paper. Yeah. Sorry?
Core.
Cord. Cord.
C-H-O-R-D.
Yeah.
Oh, tomorrow.
No, C as in cat. C-H-O-R-D.
Yeah. Yeah. So that's all I have for this class. So